Good Soul Habitat Matching, Mars Analog Mission 166, the Alan Shepard mission, with my fellow astronauts Julio Rezando, Kevin Kumar, and Alden. And this is Martian astronaut Iniya Pragati from Greenhouse Station. And today I'm going to present about the infrastructure on Greenhouse Station. And this is our habitat, and this is the Greenhouse Station. So here you can see the seven infrastructure clearly. The launch center, main station, health facility, sanitation center, engineering facility, power station, Moxie. And today I'm going to talk about the greenhouse station. This is the overview of greenhouse station. So internal design, mission technologies necessary for the operation of the installation, possible resource to generate in situ or transported from Earth, organizational structure and position, profiles and duties, astronaut training program, videos to train astronauts and resources needed for 1 week, and guidelines that need to be provided for other facilities, and the specific protocols or the routines of the facility, and protocols of safety, protocols for occupancy and entertainment, protocols for food micro protection, protocols for 3D printing, and technologies and outputs that could be applied to Earth, guidelines to be applied to the daily life on Earth, and impacts to sustainable development goals. So I'm starting the presentation with internal design, and so this is a greenhouse capsule module with a SpaceX Starship rocket, so which was built on Earth and transported to Mars. And so this it is having a 8 meter in diameter and with the 3 floors: first floor, second floor, and third floor. And on left side you can see the cross-sectional view, and on the right side you can see the 3D view. And now we are seeing the greenhouse station in detail by floor by floor. And first floor is for relaxation and entertainment hall, and a gym, kitchen, and a dining room, a toilet, and a dormitory for astronauts, and plant growing area, vertical gardening. And in second floor we are having a hydroponics area, and research room and storage room, and pump and lighting area, and plant growing area and vertical gardening. And in third floor we are having a 3D printer, and aquaponics system and aeroponics system. And we are also having a sky observation where the astronauts can observe the night sky with a telescope, and a storage room, a plant growing area, and a vertical gardening. And next comes the what we are going to do in greenhouse station. We are going to research with plants, cultivation of plants, food protection, control of soil condition, the follow sensors and necessity of the maintenance, follow inner radiation, follow the development of the plants like health or disease, and the cycle of the plant, management of cultivation, collection and discard, and identify the possible threats and the alerts, and the management and control of oxygen and carbon level, management and control of temperature in inner climate, and management and control of energy demands applied to irrigation and lighting system, management of aquaponics, taking management in water quality. And next comes the bioregenerative life support system, which is shortly called the BLSS. So which is divided into 3 compartments: the bioreactors compartment, plant compartment, and human compartment. And here you can see the interconnection of with other seven infrastructures with water vapor, carbon dioxide, oxygen, with food, the deadlock substances, the the nutrients, and all those things. And this is bio. This is also a bio. No, this tells about the microbial biotechnology-based life support system. Uh, in regulate bioremediation and biomining, which comprises no, sorry, which over concludes the materials and manufacture, manufacturing, and human habitats and laboratories, and life support system and environment control, waste recycling, and food and medicine production, and bioregenerative life support system (BLSS). So here we are having a big important question. So how to improve crops cultivation and food production in space? So the research activities proposed is the developed optimal food production scenarios for different reference missions, the defined scale, multi cropping system, and the cultivar or space idiotite, and develop the mechanistical knowledge and the predictive models, including reduced gravity and radiational dose as input parameters, and to optimize the space cultivation subsystems and define the effects of cultivation in space factors on plants productivity and quality, identify the effects of the space factors on plant hydraulic process and photosynthesis to define the requirements for environment control, and explore the ISRU to use the regolithic as the plant substrate, and explore the use of plant microbe for the growth and product improvement, and develop the systems and the producers to monitor cultivation conditions and plant growth in real time, and study the biology in multi-phases of flood systems and process in reduced gravity, and identify and solve the bottlenecks in the productive cycle, and select the species and protocols for the minimal food processing. Consider the use of the plant production systems as a tool for non-food applications. And in space relevance, it is split into both, which is short term and medium term. So next, the some mission technologies necessary for the operation of the installation are the carbon dioxide generation and distribution for the plants, earlier climate notification, time controlling, lightning system, drip system, sensors, and printing, and again the regenerative life support system (BLSS). We are also having another important question right here on the screen: how to improve space reactors and space biotechnologies. So the research active proposed on the ground and space trials, the further improve bioprocess integration, and the define optimal configuration of space photo bioreactors for optimal space bioprocess, develop the biological and technical solution for bioprocess monitoring and remote control, and testing upscales from the small size flight bioreactors run from short time to the larger sizes and the long-term performance, and perform biotech pilot test on spaceflight platforms in low Earth orbit and beyond, and explore the wider potential of the microbial biotechnological applications in the space beyond control cells, including single cell proteins, nutraceuticals, and pharma biotics, and HD bioprinting and biomanufacturing. And in the space relevance, it is divided in both of in short term, medium term, and medium long term. And the possible resources to generate in situ are transported from Earth or soil collection, seed sampling, microorganisms cultivation, fungi and microalgae for biofuel, plant growth, heat protection, energy protection, water extraction, carbon dioxide capture and treatment from Mars, and composting the waste composting, and possible resources to generate in situ and transport from the Earth. So in Earth, you can see in y and x and y axis. So x axis tells us the availability of the in situ resource, and y axis the availability of logistics resupply. And in B, you can see the comparison between lunar and Mars in atmosphere pressure, water, regolithic compression. And in C, you can see the interconnection of the in situ resource utilization, processing hardware, in situ resource, habitat, the pre and deployment cargo and crew transit, crew, bodily fluids and solids, loop, uh, loop closure and the habitat, and the carbon dioxide. And here you can see the carbon dioxide conversion strategy, carbon feedstock, and biomanufacturing host organism, and bioproduct class. And next comes the management. Yeah. So the greenhouse chief, researcher, chef, and assistant. So greenhouse chief duty is to check the protocols happening in the center, which the crews are following, and to check the crew's daily routine. And the researcher duty is to check the plant and soil health, and to also check the plant oxygen supply, and also test the seed health test, and microbiome research. And chef. So chef duty is to cook the food and arrange the menu or the meals for the day, and plan the availability and assess the crew's nutritional requirement to the greenhouse chief. And assistant. So assistant duty is to is to support the chef and check the water quality and sensors, and entertain the team with some music or dance or with some contents. And astronaut training program. So topics of training during the missions, research and breeding methods like hydroponics, aquaponics, and horticulture, first aid, 3D printing, nutrients, astrobiology, climate science, brainstorming and problem solving, and space psychology for the mindfulness, well-being, communication skills, and integration. And these are the videos to train astronauts. You can see it. Yeah, the resource necessary for 1 week. So water for one person is 3 liter, and food is 2.5 kg for 1 day, and oxygen is 0.84 kg. And for the crew of 4 for 5 days, the water required is 60 kg, the food required is 50 kg, and the oxygen required is 16.8 kg. And the guidelines that need to be provided to the other facilities, the main station, so power supply to all other stations, and oxygen supply, and also the recreational area, the engineering center, the instruments that need to be prepared, and the equipment, like sensors, pipes, and tubes. And it also needs a storage facility and sanitation center. So sanitation center is mainly on water recycling, carbon dioxide generation and recycling, composting, waste composting, and biomass protection. And in power station, energy supply and a power supply. And in health center, checking the crew's health daily and daily exercise routine, to check the crews that they are exercising daily or not, and do the first aid. If any injury happen, can go to health center and they will be taken care of first. And then comes the protocols. So specific protocols or routines of the facility. So monitoring daily routines, reduce workloads, and conduct course related to the greenhouse management at the high level of efficiency. Maintain the biosystem preventive maintenance and the good condition of the cultivation beds, and collect the data and make a report. And food protection protocol, food system maintenance protocol, space food system protocol, food processing protocol, and greenhouse building protocols. And protocols of safety. So water quality, intrusion of wastewater, virus and bacterial contamination, proper disposal of waste items, leakage of carbon dioxide into the habitat, and health issues due to the food, and microbial overgrowth, and proper soil treatment. So protocols for occupancy and entertainment are relaxing and meditation, and doing some physical activities, and observing the plants, and communicating with families and friends, and listening to some musics or reading books or doing some other activities like this. And protocols for food micro protection. So crop selection, growing medium, nutrient management, water management, temperature and humidity, lighting, pest and disease, growth monitoring, harvesting, waste utilization, record keeping, research and innovation. So these are the plants which are grown in space, the hydroponic. So the spinach, lettuce, tomato, cucumber, spring onion, and strawberries. And protocols for 3D printing, the site selection and preparation, material selection, printer calibration and testing, design and modeling, printing process, quality control, energy and waste management, post construction inspection, sealing and insulation, integration of components. Then comes the spins of technologies and outlets that could be applied to the earth. So this is TRL, the technology readiness level. These are the plastic consumable recycle, air meditation, and humanized processing, and decarbonization, energy protection and storage, e-waste recycling, soil or regolith remediation, structural biomanufacturing, biological carbon dioxide, no, sorry, oxygen generation. Okay, so and pharmaceutical biosynthesis, then biomining, then cellular food production, and these are the things which can be applied on the earth. And space architecture, hydroponics, indoor farming, solar glass, graphene, plant-based plastics, sensors, environment sensors, a carbon capture, and a bio 3D printer. So these are the things which can be applied on Earth and as well as space. And guidelines to be applied to the daily life on Earth. health and safety measures, new approaches to education, healthcare improvement, guidelines for catastrophes and accidents, and energy infrastructure, and the impacts to the sustainable development goals. So how do results from the operation of the infrastructure impact the sustainable development goals, which are uh, as below. The health and well-being, good health, training astronauts, uh, quality education, women and men balance, gender equality, water saving, clean water and sanitation, energy efficiency, affordable and clean energy, recycling, uh, responsible consumption, management, peace and justice, uh, partnership, partnerships for the goals, climate action. Um, these are the impacts which are also impacting. So zero hunger. So BLSS, which is the bio degenerative life support system, uh, research is aiming to produce the healthy and safe food products with minimal energy, water, filterations, consumption, and impact on the environment. And BLSS systems either are vegan or include insects as a protein source, and it is an exemplary development of the of a vertebrate life-free agriculture system. And the good health and well-being, PLSS systems are designed to keep the space crews healthy throughout the full mission, and via healthy atmosphere, water, food, and the nutritional compounds, and the quality education. So life support research is an attractive tool for the STEM training and education. So involving many different science discipline, for example, like food from ESA and astroplant from ESA, and growing beyond the Earth, the NASA, and as the space exploration is a program aiming at the future, it is an it is essential to educate the next generation on the topic. It lays the fundamental of transgeneration and across the disciplinary knowledge transfer, and clean water and sanitation, safe sanitation and pathogen control in confined space, and eco districts, cities with short cycling material flows, and affordable and clean energy. Algae biofuel represents an energy resource, and it is an areas of active research. Space algae biotechnology could generate naval systems, materials, and methods, also with potential applications on Earth, and sustainable cities and communities. So the 11th, uh, life support subsystems are relevant to domestic waste waste treatment, water and nutrient recycling, the both in highly populated and uh, associated environments. And BLSS can provide the solid scientific and technological knowledge to implement a vertical farming in cities, and responsible consumption and production. So natural resources will be better managed in the closed environment, also with the reduction of the pollutant emission, and increased food safety, and recycled food products remain an issue with which should be addressed at a collective social, psychological, and educational level, and many micro algae protection are already used in food supplement, cosmetics, and fuel. And this is my reference. And these are my personal contacts and in social media. Thank you. Good sir.